Okay, now it's recording now, the screen and stuff. So I hope all of you are healthy and feel very good. And today, before starting the session, I want to tell you about the evaluation process. And I ask you actually to send me your names, like in group three. uh, any of you already thought about it? Have you found your partners, your colleagues, or the ones that you want to work with? Okay, good. So until next week, please send me your groups in three. And if you are interested in a paper or something, send me also the paper, or the models that you like to work, or it doesn't it's not necessary to exactly be about like neuroscience, but it should be related to like the models that we covered in dynamical systems. So I look at the paper that you sent to me. If it works and if it is rich enough, uh, I will tell you. Otherwise, I will send you some papers to work on. Recommend some search terms for Google Scholar to get us started, or the name of a journal. In Google Scholar, you can, yeah, I mean, mostly it's going to be like, uh, well, we have some books, right? So one of them is Steven Strugatz. You can follow him. One of them is Eigen Ijikevich. Eigen Ijikevich. And you can find tons of models and works in the book by Ijikevich, Dynamical Systems in Neuroscience, like, for instance, Fitzhugh Nagomo, which we will talk about today, or Hodgkin Huxley, or whatever. And also like journals, like you can search like in Nature or PRL, like PRL, uh, or Trends in Neuroscience, mm, or yeah, whatever. You can just search for that if you are interested. Otherwise, I will send you papers or works that is good enough and rich enough to work on. Okay, so I will also email the people, everybody, all of the participants, to send me their names and the project that they are interested in. We do not have a suggestion for a topic. Are you going to give us different suggestions and that's when we can choose? Yes. Yeah, I will send you different suggestions. You can pick one of them, the easiest one, for instance, if you are interested in, or the hardest one, and then you will basically analyze them with the dynamical systems point of view, like uh, finding the fixed points, finding uh, the like solving the differential equations by Euler method, which we are going to talk about, and talking about like qualitatively about them, drawing like in the phase plane, and after that, like just a report that you can actually apply the knowledge that you got from this course on a new paper that you are dealing with, and you have the option to choose. Yeah. Is that good? Or if you have a suggestion, tell me. You're welcome. Okay, so let's now. You don't have my desktop, I think. My screen. I try to. So okay, great. So let's start with Euler method. Not this one. Hmm. Yeah. Okay. So this is the book, Nonlinear Dynamics and Chaos, and you have my screen, right? So if you wanted to interrupt me, please just unmute and tell me whatever you want. So we want to solve differential equations in general. For solving differential equations, we prefer to do it analytically because it's not computationally uh, expensive. Therefore, we try to do it analytically, but most of the time it's very hard. Therefore, we need numerical solutions for that. So there are several algorithms, but the basic one is its name is Euler method, and by improving this Euler method or in several ways, you can reach more accurate answers. But we just if we just know about Euler method, we will be able to actually solve our differential equation. So the point is that in Euler method, we say that okay, we have a function like this. This is the exact function of, for instance, x, like f of x with respect to x, or y with respect to x. So x dot is the change in that. So we have these open circles here, and we say that if I get closer to that, it's like the idea of limit that you faced in high school. So if I want to reach like again, the idea of linearization is governing here. If I want to find the slope of this curve around this circle, around this open circle here, I will just get closer and closer and closer until I am in a very close neighborhood or or proximity of this point, that this curve is not can be actually viewed as a line. Therefore, I will say that the delta of x over delta of t will be the slope of that the slope of the tangent on that point on that curve. So this is the basic idea. For these, like in more accurate way, we say that we want to find the x in t naught plus delta t. Like for instance, here we have t0, and then we want to find it in t1. This is the exact one, x of t1. If you solve it analytically, then you will find this one, but most of the time we cannot. Therefore, we need to do an approximation. And for instance, by Euler method, we can find the point like x1 over here, which is very close to this exact solution of this equation. But if we change this delta t here, like getting closer and closer to this t naught, then this difference is going to be less and less and less until the moment that we can approximately say that it's equal to that. So for this, we say that this x of t naught plus delta t will be x naught plus f in that x naught, which is this. So we are seeking for this solution, but we use the f of x naught in here times that delta t. So this is the basic idea, which I think you are familiar with, but for this Euler method, we can just say that actually we are discretizing the differential equation, because in differential equation we have x dot equal to f of x, right? X dot is the first derivative of our function x with respect to time, and therefore it is dx over dt. So if we want to discretize it, instead of dt we call it like delta t. So therefore dx will be delta t times f of x, right? And x is equal to x naught plus x dot, right? Therefore it is x naught plus f of x, which is our function in x naught, times delta t, which is coming from that discretizing idea of dt instead of dt, because dt is coming from those mathematical assumptions which we have a positive value like epsilon, bigger than 0 but very 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 close to 0, coming from the concept of infinity as epsilon goes to 0. Therefore we have that dt, but for discretizing it we just call it dt, and this dt can have like it is showing the steps of our solution, like 0.1 or 0.01, like, or 0.001, this kind of things. So now we want to solve one of them, right? So if I want to go to the practice sheet, in practice sheets, so in the practice sheet we have this Euler method. For this Euler method we have several cases. Like for instance, take this one. We have dy over dt, which is y dot, right? Y dot is equal to 3 minus 2 times t minus 0.5 times y, right? So this y dot is a function of y as well as t. And we have this is the initial condition here. In the initial condition, this is the representation of t, like t naught is equal to 0 and y of t naught is equal to 1, right? And then by knowing this, we are going to approximate the value of y in time 1. So we know the differential equation, which is this. We know the initial condition, which is this. And we want to approximate the value of y in further steps of it. So in general, we are going to write the code here, but it's this is the Euler method, which is written by Devrim Klik. It has actually I said all of them, but you can it's an interesting thing that he tried to compare this Euler method with gradient descent, which mostly is using in neural network and machine learning stuff. So it's just interesting that this method is very similar to gradient descent, okay, in statistical learning. So the point is that the approximation here, which we are doing in gradient descent, is tries to find the x for which the function has a local minimum. On the other hand, when using Euler method, we are giving the x goal, right? We are talking about future, and this is the one that is or here it is x goal, or you can say t goal. It's just a name, right? Y with respect to x or y with respect to t. So by knowing, for instance, at time 1 we are going to calculate y. So for instance, in this example here, for solving this, we say that dy over dt is equal to delta y over delta t. And then we times this dt or delta t to the other side, like delta t times this function here. And what is dy? Dy is also delta y. It means that y1 minus y naught, or y2 minus y1, or y3 minus y2, right? Step by step. So in our work here, so we again use, for instance, NumPy as a library, and we use so this is not a thing that actually we need to use. So this is the R. This is another one. So so for y, we say that we have like a lot of an array with the size of 6 of ones. All of them are 1. Why I chose 1? Because here we have y naught is equal to 0. Y naught is equal to 1. So I actually didn't need to put all of them to 1, but all of them are going to be changed. So just the first one is important here. So it is 1. And t, which is our time, is 0. It is starting from 0, and then we change it. And dt or delta t, we can take it like 0.2. Why I took it like 0.2? Because here it said that use 5 steps here. And 5 steps means from 0 to 1, I should go like step by step, which is equal to 0.2. So 0.2, 0.2, 0.2, 0.2, so 5 of them, like 1 minus 0 divided by 5 will be equal to 0.2, right? So I do a very simple loop, for loop here, like I have an I, like an indicator or index here, which is in the range 5. So it means that it is starting from 0 to 5 step by step, by like increasing, like increasing by 1, like 0 plus 1, and then 1 plus 1 equal to 2, and then 2 plus 1 equal to 3. So this is my delta y right here. For instance, here I have, so I just try to write it here. Maybe it works. Where was this? Okay, it's not important. So it's like delta y, like delta y is equal to y of I plus 1, which if I put the I is equal to 1, right? minus 1. So if I have this delta y here, then this is going to be delta y, and this is the denominator of delta y over dt, and this dt here will times the whole function. And the whole function, as we can see here, it is 3 times minus this 2 times t, which this t is in the I step, and this y is also in the I step, and therefore we use it like ti and yi times dt y for finding y of I plus 1, the next step. After calculating y, we say that now we want to go to the further step, and we use ti plus 1 equal to ti plus that dt. So this is going to be 0 plus 0.2, and therefore ti plus 1 is going to be 0.2. And next time, this ti will be 0.2 plus 0.2, then ti plus 1, which is t3 or t2, will be equal to 0.4, right? And then printing them, printing ti and yi. And for this, this is your ti, which is your t0, t naught, and this is your y naught, which starts from 1. And by governing that this equation, this is our differential equation over here. The next step, t1 will be 0.2, and then calculating this, y1 will be 1.5, and so on. And you will see that it is exactly like this. So I actually did a mistake. I should, because of this for loop, I should use I should actually use maybe I can do it here now, like instead of this. That the size of my matrices are not. I don't think. I think I will get an error. Yeah. So I should change them, but you got the idea, right? If you just change it, for instance, to 7, it's working. So any question here? No. I think you are okay with that, but if you have, just let me know. So this is the next one. The next one is y prime equals to y sine of t minus 1. Again, the same. Again, you have the 0 over here, which is your t naught, and you are seeking for the value of y in t equal to 3. What is the step of u? The steps are, your steps are 0.5, therefore 3 minus 0 equal to 3. Therefore 6 steps it takes to reach with these steps it takes 6 steps to reach this t equal to 3, right? So again, for calculating them, you have again your initial condition is 2, therefore you put y equal to 2, all of them. You can just take the first one, otherwise it works, it's enough. And t, like the zeros, it starts from 0, and this is your h or dt. And again you have a for loop, and this is again your delta y, which you always have this part, right? In all of your differential equations, you have y of I plus 1 equal to y of I plus dt times your equation. So this is your equation which is changing. These are same, this is also same, and this is also same. Just this is changing. So, but the important thing is that you are trying to find the I plus 1 with calculating I. Actually, you can find very more efficient ways of calculating this, but it works. I don't think it's an evolution. It's an efficient code, but it works. So you again have this y sine of ti here minus 1, right? So again you say this, let me actually plug my laptop, otherwise it's going to... Okay, sorry for this. So again, you can find y of I plus 1 with this, and you can just print them, and this is going to be your solutions so you are actually solving differential equations like this numerically with Euler method, the very simple one. And by increasing this t, you will see again that you are calculating new values of y's. Any question? Okay. So
is there a computational benefit to doing this compared to integrating the equation?
sorry,
And
may you say it again? I didn't hear you.
so, is there a computational benefit to doing this compared to integrating the equation and then finding the values or the one value we need?
It was very noisy, but if I didn't get that. If you write it, it was very noisy. The computational or other benefit to doing this? Yeah. You mean different algorithms, right? I mean, so this Euler method is one of the most basic ones. If you change your algorithm, for instance, for taking this improving, taking this can find it. So if you want to use the improved version of Euler method, this improved Euler method, you will come with this idea that you, instead of just getting closer to this point from one side, you can use two different slopes from left and right, and then taking the average of them. So this is the improved one, and you can see that actually you will have other methods like fourth order Runge-Kutta method or second order Runge-Kutta method, that they are different algorithms, and they are more accurate. However, it just takes more computations. If you are seeking for a different algorithm, yes, there are a lot of algorithms that you can use. And yes, you are right. It's not that much efficient. It's not that much. Uh, what is what yes, this is here for instance, you can see that in Euler method, those errors will be decreased with delta t, but in your improved Euler method that you are taking from the both sides, it's going to be decreased with the second order of dt. Therefore, it is faster and it is more accurate. And if you change your algorithm to other ones, then it's more accurate, but it takes more computations like this, calculating these kinds of things, coefficients, and then calculating your x of n plus 1 with this xn plus this, but it just takes a lot of computations. All of them is same as this, but all of these ideas is xn plus 1 calculation with the help of xn by the by discreting your differential equation. So if you are seeking for a new algorithm, there are several of them. Yeah. Was it the thing you were seeking for, or? Okay, good. Uh, so if you thanks for your question. It was good. You should cover these things as well. So here again with this y prime, so the difference here is that instead of t you have x. So this y prime is dy over dx. Therefore, for your new differential equation, you want to approximate y, the value of y, at x equal to 8, but your initial condition is 3. Your initial condition it starts from 3. So therefore you just do the same thing over here. You say my y is equal to 3, like always. 3 times 1, therefore it starts from 1. And your x is also equal to 1, which is, am I right? It starts from 1, your x. It doesn't, right? Yeah. No, your x should start from 3 and ends to 8. Okay, I should change this, but it's not that much important again. Your dx is that 8 minus 3 over 4, because it says that it's going to be 4 steps to approximate it, and so these are your steps. So again, you come with this differential equation, which you write this xi plus 4 is here, this xi plus 4 over xi minus yi plus 1, right? Xi minus yi plus 1. So this is your differential equation times dx, which it was dt, plus yi. Then you will calculate yi plus 1. And then you just increase your x with the steps of dx. And again, calculating and printing them, and you will have these values over here. So it just depends on these initial conditions. If you just change this x to like this one, like 3 times np1s, then your initial condition will start from 3. But here with this situation, it starts from 1. And And here again you will have this different equation, which the idea, like I think the most different thing is about this difference, like minus some number like this and some number like this, which you just say that I substitute this number from this number and divide it by these steps. That's all, and put the equation there. So with this you will see that so your t will start from this is your initial condition, and your dt is equal to this, substitute that and over your steps, number of steps, and your y will start from this number, which already mentioned here, and again your for loop. This is your differential equation. This is t squared over y squared plus 1. All of them are the power of your exponential function, which you can again say np dot exp, which is your exponential function, which means e to the power t squared over y squared plus 1 minus y I, which is this, right? And again you calculate them. And so one thing that I did wrongly, for instance, here I forgot to write yi, or I forgot to write ti, and this is going to be, you will have some errors here. But if you change them like yi, and if you change the t to also ti, then you will have the right answer. So this is important to just take, just to be paying attention to these things, not using a continuous thing as a sequence in your element, right? So, and these are your t's, your times, and these are the values of your thing that you can see that here is exactly the same, right? So that's it. If you don't have any question, we can go on. Okay. So let's talk about this limit cycle, which is a very interesting thing. So this limit cycle, we talked about closed trajectories last time. We have three types of them. Let me make it bigger. So we have three types of them, but this half stable limit cycle is the very exceptional one, so we don't really deal with this. We don't have it that much. We mostly have stable limit cycles and unstable limit cycles, which we showed them like dashed for unstable and like a line for stable. And if you see if the state of your system is inside of it, then it's going to be attracted to this from inside. Therefore you will see a kind of spiral, and from outside you will see these kinds of trajectories. And if it is unstable, then it is repelling. Therefore you will see this focus, like stable focus here, and repelling from outside as well. And if it is half stable, then one of them is repelling and the other one is attracting to that, but this is not happening that much. So the difference between limit cycle and our periodic solutions is that like these kinds of periodic solutions that we had in linear systems, because we had ax plus by for x dot, and that was a linear, because it was just first first power like ax. We do not have ax squared. We do not have a function over here. Therefore, it is a linear system. It's just ax plus by. That's all. And if x of t is one of our solutions, which we saw in the phase plane, then c times x of t is also another solution because it is a linear thing. And limit cycles doesn't happen in our linear differential equations. It should be nonlinear. And one of the good examples is our logistic equation. In logistic equation, if you remember, it was about the population, for instance, of a bacteria, which we had some foods in a dish, and then they grew up, and then it depends on the capacity and stuff, and we draw these things. And one of them here, it was our unstable fixed point. The other one was our stable fixed point. And you can also see it here, right? So if I put this x dot equal to 0, then x is equal to 0 is one of my fixed point, which is this. And if you calculate the derivative of it, it will be negative, therefore it is unstable. And the other one is 1 minus x squared is equal to 0. Therefore, x equal to 1 is going to be another fixed point. Then 1 minus 1 is equal to 0. And if you again take the first derivative of it and put 1 in your first derivative, like f prime, then you will see that it is going to be negative, and here you can also see that the slope of this curve and graph is negative, therefore it is stable. And it doesn't make sense for like populations like less than 0, right? It doesn't make sense. And if you just say that x dot equal to this, and I have another function like y dot equal to 1, then you will have an uncoupled but nonlinear differential equation. Nonlinearity is coming from this, for instance, x2, x squared, or better to say x cubed, right? X cubed here. And so if we want to use our p-plane, you can also do these things, right? So I suppose that actually you are with me and you are doing this as well. So if I go to p-plane here, so in my p-plane, if I put x prime equal to x times 1 minus x2 x squared, so this is based on MATLAB, therefore we put the power like this. So, and y prime equal to 0, and these are the minimum and maximum values, and I don't have any parameters, or I don't need to put any parameter here for expression. And if I graph the phase plane, I will have something like this. So with this equation here, x prime and y prime, my phase plane, which is y with respect to x, are going to be like this. So this is going to start from 0 and ends at 1. So if I have like if my population starts from here, for instance, then all of them will attract to that fixed point. So this is actually my fixed point here. So if I so this null line is actually my fixed point. This red one is my fixed point, the family of my fixed points, and this is also the family of my fixed points. And you will see that all of them will attract to this one, right? Repelling from 0 and attracting to 1. And if it is bigger than 1, if x is bigger than 1, then by that differential equation, it is again absorbed to this fixed point. So you will see this line like x equal to 1 as your fixed point. And so here in page 220 by Strogetz, let me actually close them. So here you will see these limit cycles, as I said, like stable and unstable, and which it actually does not happening in the linear systems like this. That if it is like if you have x dot equal to ax, and if x of t is a solution, then c of x of t is also a solution, then you will have this linear system, and you do not have examples here, but you need some nonlinear equation like this logistic equation that we talked about. And so Hunaid also asked about like this radius and angle stuff last week, and it's interesting that instead of writing like something like so here we have this x dot, and you just put this x like replace it with r, then your r dot will be equal to r times 1 minus r squared. And if you replace this y dot equal to 1, then your theta is equal to 1, right? So why we do this? We do this because we want to have we want to find like a geometric viewpoint. So we just say that this r is the representation of radius, and this theta is the representation of our angular. So we have radial and angular dynamics, and they are uncoupled, right? Because we do not have any r in theta dot, and we do not have any theta in r dot. Therefore, they are uncoupled. They are not coupled. So with that same argument, you will find the r star equal to 0 and r star equal to 1 as your fixed points, which you can also talk about the stability of them. And if you put this r equal to x2 plus y2, then it's an equation of circle, right? So if r equal to x2 plus y2, then your y and x is going to be like you have two kinds of fixed point, r equal to 0, therefore y and x is equal to 0, which is this, and y and x should be on this circle to actually satisfy r equal to 1. So this circle is the representation of this point over here. R equal to 1 is equal to x2 plus y2. I just changed the names, right? It's just for simplicity. X2 plus y2 should be equal to 1, and we know from higher school that this is the equation of a circle. So this is why we call it like circle. And if it starts from here, like as we saw here in our face plane, if it starts from here like bigger x and bigger y's or whatever, then it is absorbing to this limit cycle. If it is starting from inside this neighborhood, then it is also repelling from this fixed point, which is 0, and absorbing to this limit cycle. This is why we call it limit cycle. And if it reaches to this, then it will stays over here. This is the idea behind limit cycle, is repeating state of the system. This is why we can use it, for instance, for our spiking neurons. And so this is why we call it like circle. However, it's not always a circle. It can be another, like in another way, and we are talking about it now as van der Pol oscillation. If you have a question until here, okay, no. So van der Pol oscillation. Also Hunaid asked another question about our pendulum, like x dot x double dot without this term plus x equal to 0. And if we just add another term like this, mu times x2 minus 1, then we are adding a nonlinear damping. And this nonlinear damping tells you that actually this x2 is also always positive, right? So it's always positive. So if x is less than 0, then this term is negative. It is less than 0. Therefore, if x is less than 1, then x2 minus 1 is less than 0. Therefore, you have a negative term here. Therefore you have a kind of damping. However, you will have a kind of negative damping, which means pumping. It's an interesting thing. And if it is more than 1, then this is positive, and you will have like the normal damping. And this is just a model which tells you that actually if your amplitude, like you will have a kind of wave like x with respect to t, which we saw, and we are going to visualize it now actually. So if you have large amplitude, then this nonlinear damping is taking it down, and if it is a very small amplitude, like less than that, then it is increasing. Therefore, there's a kind of fixed point, or better to say limit cycle here, which plays the role. So here in this example, limit cycle is not a cycle, and the waveform is not a sine form anymore. So if you wanna, for instance, if you take something like xt is equal to this, then you will have this oscillation like sine form or cosine form here. However, in van der Pol equation, which is this, which we are going to actually use our BD tool for visualization, our waveform is not like a sine anymore, and our limit cycle is not a cycle anymore. So let's check this over here. So if I can just tell you that you should again do this at path here, and find the path of your BD toolkit as well as its models, both of them, and then put like help van der Pol oscillators, and then this is going to be open for you. It is the author is Stuart Heitman, and the code has been written by him. And so for this equation here, we have this x dot, right? We just can change it to, for instance, to u. And if I put x double dot equals to y dot, which we saw that for linearizing this, for having the same form like x dot equal to f of x instead of x double dot, we put x double dot equals to y dot, or it's just a name like u and v, so it's just the same. So if I want to visualize it, I can say that my equation here my equation is going to be like this. So your u dot, which is your new variable which you actually created by v double dot, is equal to v. Sorry. You are so this v is the representation of x dot, and v dot is equal to x double dot, right? So then you have this equation over here, and then this term like 1 minus u2, which you can play with this u like less and more than 1, and put this less than 0 or bigger than 0, like negative and positive forms, and that's all. So I think that you actually did this. If you want to just use it, you need like kij equal to, put it like 0 or 1 or whatever, and then write the system to van der Pol k of j and be the GUI system. After that, if you go to time portrait, you will see that if I have these parameters, so all of you did this, right? I have some questions here. You know how you type the equation in p-plane? Yes, I will show you. Okay, so you don't have this problem anymore, right? Because Anika answered you. So what is your equation? Then I can help you. A different model. If you exactly type this, then you will have the logistic equation. But if you want to have any kind of model, you can actually access its face plane by p-plane software. But now we are talking about this van der Pol. If you need time for that. Okay. Okay. I continue. So I hope you actually did this BD tool, and if we increase the parameter like a here, then our parameter is this, right? So it is minus 10, for instance, and we are just going to increase it, and by increasing this, you will see that our actually I need to calibrate this. So then you will have this kind of form for u and v for your differential equation variables. So again, if you increase it, then it is kind of similar to sine, but it is not that form. It is like a very sharp, like mostly they call it like like sharp teeth, shark way, kind of. It's just because of the shape. It's not like sine anymore. And if you go to face portrait, then your face portrait also is not a cycle, but it is pretty much has the same behavior, if you start your condition inside this, then it's going to absorb and attract to this trajectory, and it is just doing it over and over, which is coming from this very interesting relaxation oscillation named van der Pol oscillation. And if you change the initial condition outside of it, like for instance, if I take this v to minus 3 or whatever, so this v, if I put it like minus 4 for instance, then it starts, maybe I should calibrate it, yeah, then it starts, and it is going to, like it's again very interesting and important to talk about the speed of it. You will see that very close to these points that it is uh, it is actually governing by the null lines, and very close to these points you will see that it's very slow. But when it is far from it, or here for instance, when it is far from it, then it is not slow, it is very fast, it is fastly going through these trajectories. So this is why we say that there's a kind of wind flow here. You will see these vector fields, like these gray things here. These vector fields are big, but here if you go to these points, it is very there is no speed here. But here you will see that this is so much fast. So it's like a wind flow that put this state of your system to this point, and then it is oscillating, and oscillating here is fast and here is slow. So for showing this, maybe it's better to go to this maybe it's better to go to this page, which was page 213. I am wrong, actually, it seems. Yeah, here, 18 it was. So I will have this y and x, and my state of my system here is very fast, and it goes and actually crosses this null line. So this is my null line. This is my null line, and it has this shape because it has a cubic form, and it is crossing this, and this crossing is coming from those differential equations, which if you want to have the limit cycle, then actually your x should decrease, and therefore your x dot should be negative, and by this you will find that this y, which is equal to f of x, which is coming from some simplification here, like this is my real form, and if we do this math, which is not important for you, at the end I will have this formula for x dot and y dot here, and with that you will see that it is crossing your null line, but the wind of those flows, like those vector fields that we saw, it just push it to this null line, and it comes and it follows, and then there is no barrier here, and then you will see again a fast change to here, and this is actually your oscillation. It is just going this part, which is fast, sorry for this part which is fast is the upstroke and downstroke, which is very fast, and this part which is very slow are the moments that are in the peaks of your waveform actually. So if I want to see this, if I also want to see its bifurcation, which is very hard to visualize, maybe here, maybe if I close it and if I again see the bifurcation here, and if I put it to 3D, and if I change A to minus something, and if I calibrate it, and instead of this K of J, I should have A because I am changing A. So A is like something mu, right? So here it is written like mu, like x dot is equal to mu, and here it's just a name. It's just the coefficient of it. So if you will see that with this initial condition, it just again goes to fastly going to this point, which is the ghost of your fixed point. But by changing your parameter, you will see that you will have a very different trajectory over here, and you will have a limit cycle. Actually, the bifurcation is the moment that your limit cycle has been created. By changing the parameter, you will see the bifurcation, and after this bifurcation, you will have this oscillation here. That was a lot, that part, but this part, which you have this oscillation, this limit cycle is the representation of your oscillation. So this was van der Pol oscillation, and if you don't have question, then okay, so it seems that you solved the p-plane stuff with the help of your colleagues and classmates. And what I was searching for, for Fitzhugh-Nagomo model. So this model, Fitzhugh-Nagomo, this was like, this Fitz was a very big guy and great guy, and one of the leaders of neuroscience, giving the models, and their students actually came with the idea of Maurice-Lécar model, which Maurice is a very great woman, which was trying to model in the muscles, and this is its paper. And later, this is for instance one of the things that you can work on it, one of the models that you can work on it, like Maurice-Lécar model, and you can talk about the dynamics features of it. So this is for instance one of the suggestions if you don't have anything in your mind. And so Maurice was one of the great and the leaders of the Maurice-Lécar model of a spiking neuron, which is kind of a reduced and simplified form of Hodgkin-Huxley. And this they were the students of Fitz-Nagomo. Also, I can tell you that actually this INAP model that mostly is using it is actually Maurice-Lécar model. But Fitz-Nagomo model has this form, like you again have the change in voltage, your membrane potential, because you are talking about the action potential, the generation of your action potential. Action potential here means passing the threshold. Passing the threshold means that you will have a spiking behavior. Then you can actually explain the spiking of your neuron by bifurcation, by limit cycle and stuff. So the change in V, the change in voltage has this differential equation. I is your injected current, which you can put it like in 0, and the W, like if you remember in Izhikevich model as well, W is your is your recovery variable, which again it has some features like B and C, some efficient, some coefficients like B and C, and by changing them you will have different things. And again, the point is about the simplicity, and you've seen in the lectures these null clients and the way that you can separate them to 4 different regions and talk about the behavior of your system. And if we wanna see it now here, so again we came with this idea like writing so you see that again you will have this Kij, so you can just put it like 1 or 0 or whatever. It's if you want to work like in a network of neurons, it's important, but we're not seeking for that for now. So I put like Kij this, and this is my system, and this is my GUI for visualizing that. So it is again written in another like notation. It's not important again. So if we go again to our time portrait, like we wanna see V with respect to T, then if I inject the current over here, I will see the spike, right? And it is, if you again see here, it takes less computation than Hodgkin-Huxley model, for instance, and still is informative. It tells you about the spiking behavior. It tells you about the phase portrait, which again is your limit cycle in your phase portrait. And if I want to see the bifurcation, for instance, here it is. Yeah. If I want to see the bifurcations, so I want to have, instead of this Kij, I take, for instance, I, like my current, and by changing this, you will see that after a threshold, the whole idea of a spiking neuron is this. After a threshold, you will have a limit cycle. This limit cycle is telling you that your neuron has the state of spiking. Here is the birth of your limit cycle. So this is the bifurcation point, actually, that your limit cycle has been created, and then you will you can also see it here, right? You don't have any limit cycle here. You don't have anything here, but by injecting the current, everything is different. After a certain point, you see that now a kind of a spiral is creating, right? So it's very important. You see that the eigenvalues, actually here, the eigenvalues are can be imaginary, can be complex, and if it has complex conjugate, then you will see these spirals. But if the real part is positive in your eigenvalues, then you will see these limit cycles and this behavior, actually, which is the representation of your spiking neuron. So this is the Fitz-Nagomo model, which it's, for instance, if you want to work on this, you should talk about its face portrait. You should talk about every kinds of details like the vector fields, the speed of again the speed. You see that here, for instance, the speed is much more bigger than these things. That this region was the region that actually the spiral has been created, and this is like the ghost, which is coming from the idea of your fixed point. And this is why it's very slow close to this and close to that, and it's very fast here. And the way that it crosses the null lines and finding the null lines and analyzing the regions of your face portrait and finding the relationship between the bifurcation and the spiking behavior of your neuron, and so on. So if you want to work on the models of spiking neurons, it's like this. If you want to work on like the models like the network of your neurons, you can have different, like you can have, for instance, 20 neurons with different connectivity, and they are acting on each other. We will talk about these excitatory inhibitory things, and the dynamics of them will be different, and all of them have different fixed points and different behaviors. And therefore in group 3 you should actually report the things, the dynamical behaviors and features that you can understand from the models, or the models of single neurons or networks of neurons, and report them. So this was the Fitz-Nagomo, and 122 it was this, I think. Yes, or maybe this was the page, I think. Yeah, okay. So this session is kind of finished, and if you have I just forgot to tell you something like that. Just let me just finish this. It's very short. So that logistic equation. So we understood that actually how to solve differential equation with Euler method. Uh, we talked about discretizing them and using the steps. And if we have like a logistic equation like this, then we can use the same one. We have r equal to, like, our initial condition can be 0.2 or whatever. It's not important. It should just be bigger than 0. And after that your time step are zeros. Your dt can be everything, but if it is less, then it's more accurate. And again, in the for loop, you will write your logistic equation. Your logistic equation, its differential equation is always we have this part, right? We always have this part. So this is actually your delta r divided by dt, or delta t, times your differential equation, which is this r times 1 minus r squared. And your time steps is increasing like this, and you just print them. That's all. So if you do this, then you will see that actually with increasing the time, your population is growing and growing and growing, and it's not enough. Actually, it's not enough a step, because it should reach to 1. So we can actually change it. Instead of this, I can write like this, like 120, and instead of this t, again I can have like this, and the t can be good like this, and then you come with this idea of your for loop, which I do not think it works actually, because I probably doesn't work, but let me try. So if I just put it to 100 for instance, or 180 to just have 80, yeah, you see that after these time steps you will have this very close to 1, so it is absorbing always to 1. So this is, if you just plot them like r with respect to t, then you will have exactly the same plot. Yeah, so any question now? How many lectures videos are still left? So I saw actually like you can follow the websites of the university, and it's going to be finished, like the lectures are going to be finished at 18th of July. But as Professor Pipa said, 4 weeks after the last one, you will have the time to hand on your reports for the evaluation. Uh, but uh, but if you bring it sooner, then I can I can correct them sooner. So uh, it's better for me as well if you bring it sooner. But until that, I think we will have 4 lectures probably, because we have still 1 month. So maybe 3 or 4 lectures and videos will be uploaded. You're welcome. Yes, I will write down formally and email all of you, all of the participants, and for your report will be your basic the basic part of your evaluation. But so it's in group 3, and it can be just 10 pages, so it's not that much hard to do that, right? So I know that this course is an advanced course, and you should know a lot of things like working with differential equations analytically and numerically, and understanding the dynamical systems viewpoint, and understanding its relationship with neuroscience. And it's quite a lot of work, so I understand that. And but we just ask you for just a report like in 10 pages in group 3, so it does make sense to be able to do that. And the grading scheme will be more like just just very normal things, like fi- just showing that you understood the stuff in a very correct way, like fixed points, like bifurcations, uh, like solving differential equations by Euler method, like these very simple things. And uh, and and using these BD toolbox for some of your works, or p-plane for your works, and submit the figures and the phase planes that we need know about the null clients, we need to know about the vector fields and stuff. So if you just show in your report that in your work you could work with them and you could understand them and you could take the result, like writing a story based on these dynamical systems viewpoint that you got about those models or about those works that you are interested in. That's all. So if you just do these very normal things that we covered during the lectures and the tutorial sessions, then you will take the total point, definitely. PRL is like well, we have several. It's not important. Like we have mm, uh, so the physicist society of US, they have a kind of journal, and the most famous one are PRL, but it's like a letter. L stands for letter, and it's just in 4 pages, for instance. It cannot be more than 4 pages. So some several models in neuroscience you can find in PRL, but you can also find in another thing like PRB, for instance. It's another one. So it's not important. I mean, I just said the things. You can search for whatever you want, or PNAS, for instance. PNAS is something that maybe you can also find. I can tell you that forget about PRL. Yeah. Tailor expansions in previous tutorials. Yes, I talked about it, but the better one is by it's a video by three blue one brown. It's fantastic for learning and for visualizing. However, you do not need Taylor expansion. Actually, you do not need to understand it that much accurately and very precisely, and just we just need Taylor series for linearizing close to fixed points and equilibrium when we have nonlinear behaviors, and for that we just need to use the first derivative. That's all. So you can forget about Taylor expansion actually at all. And if you just use the first derivative for analyzing stability of your fixed points or limit cycles, then it's enough. Yeah, good to hear that you are actually happy as well. Okay, so if you don't have any further question, then let's say goodbye and time to go, and wish you a great weekend. You're welcome. Bye.